Good morning, everyone. I'm glad to be here. I'm going to introduce the multisymplectic unscented Kalman filter for nonlinear estimation. And I'm going to talk about the motivation and the variational unscented Kalman filter for the finite dimensional case. And then I'm going to talk about how to control uncertainties, especially the Gaussian distributions. And finally, the multisymplectic unscented Kalman filter under the framework of field theory. So why do we concentrate on the estimation of mechanical systems? Because filtering is a major concern in mechanics and control. And because we know that uncertainties or stochastic noises always exist in the physical world. So we need to relate the deterministic formulation with the collected data or measured data to better estimate the real states of a system. And many outstanding scientists have contributed to this problem, like a Kalman filter for linear systems and extended Kalman filter based on Taylor expansion and the unscented Kalman filter. But they all focus on the Euclidean space, the flat vector space. However, we know that many systems are actually living on a nonlinear manifold, like Lie groups, vector bundle, fiber bundles, and so on. So we are concentrating on how to establish estimation algorithms on in these settings. And we first start with the continuous time dynamics. We need to determine a Lagrangian, and we define the action functional, and then we derive the continuous time equations of motion. Here we derive the continuous time Hamel equations. And but most of the time we need the discrete formulation, and we discretize the Lagrangian like equation 4, and we determine the discrete action sum. And finally, by adding stochastic noises, we can obtain the perturbed discrete Hamel equations. You can see that there are noises in this equation to depict the stochastic perturbations. And this is different from previous works because it's established on the Lie algebra. But previous works usually use this one, which is formulated on the Lie group, and this naturally brings more complexities and computational burdens, and we avoid this. So how do we establish a estimation algorithm? We need two steps. The first one is the prediction step, and the second one is the measurement update. The prediction step produces a priori estimation on the Lie algebra. First of all, we sample some points called sigma points, and then we propagate them using the discrete variational equation like this. These are sigma points. This S stands for the state related with the state, and this one is related with the noise. Then we can derive the mean and the covariances, and then we have the priori estimation. It is called priori because we have not used collected data, so we use them in the second step, the measurement update. In this step, we produce a posteriori estimation by encoding the collected data information into the dynamics. And here, we construct the measurement model like equation 12. It looks simple, but it's more natural in practical applications. For instance, when you tackle the problem of attitude estimation, the gyroscope only provides the angular velocities. That's a Lie algebraic element rather than the attitude, the Lie group elements. So we similarly sample some sigma points and propagate them. Then we can compute the mean, the covariances, And finally, we get posteriori estimation. You can see that here we use the collected data or measured data to correct the priori estimation. And until now, we have posteriori estimation of Lie algebraic element, and we want to reconstruct the Lie group elements from them by the reconstruction step. This is different from the deterministic formulation because here we use the posteriori estimation to reconstruct. And here we give an example, the satellite attitude estimation problem. Here's a cubic satellite, and we collect data from real world, and we want to estimate the real states of this satellite. And in the middle is the proposed method, and this one is the methods from previous works, others' works. And you can see that in the first row, these two, red one and the blue one, is the method from previous works. They are able to estimate states, but they show some error, large error. And in the second row is our proposed method. It looks much better. And we evaluate the performance by 3 indices: the velocity error, the attitude error, and the mean square error. For example, the angular velocity error, the 4 curves at the bottom are the results from our method, and the blue one and the red one are from previous works. You can see that the velocity arrows of the proposed method is up to 3 orders of magnitude lower than that of previous works. Similarly, you can we compare our method by a mean square error, and these are our methods, and attitude error. So and next we generalize our method to the non-holonomic case. And the problem is, how do we deal with non-holonomic constraints in the filtering dynamics, and how to deal with the singularities brought by these non-holonomic constraints. The singularity here is referred to the singularity of covariance matrices caused by non-holonomic constraints, because we need to compute the covariances during the filtering process, but these non-holonomic constraints will make the covariance to be singular, so we need to deal with them. The technical details are not presented here. We just give an example, the classical Chapeligian sleigh. We collect data from the real world with they are data with stochastic noises, and we want to estimate the real states of the sleigh. You can see that the estimated trajectory looks good. The classical small heart curve and big heart. And until now, we have constructed estimation algorithm, but actually there is an interesting connection between the estimation based on variational integrator with information geometry. Following Barbaresco and Guy Belmont, we studied the reduced dynamics of Gaussian distributions. Here's the equations of motion of Gaussian distributions, and we use them to tackle the computer vision problems. In particular, we combine the variational integrator-based estimation algorithms with the geometric structures of covariances in a video, in image frames of a video. And actually, we use Gaussian distributions in filtering process to track Gaussian distributions of images, like shown in this figure. We can compute covariances of every image frame to track this stock along each frame. And what's more, we want to generalize the filters. We want to how to design a field theoretic analog of the well-known Kalman filter. In fact, we need multisymplectic geometry from classical field theory. First of all, we need to determine the continuous space-time dynamics. We determine the configuration, usually a fiber bundle, and physical fields are smooth local sections of this bundle, fiber bundle. And we determine the Lagrangian density. For the geometrically exact beam, the Lagrangian reads like this. And we need to discretize the space-time. The spatial variable is the one-dimensional space variable here. And finally, we obtain the discrete space-time dynamics, the perturbed discrete field theoretic Helmholtz equations for geometrically exact beams. You can see that there are stochastic noises in this equation here, here, and we propagate the sigma points using this equation. And after some process, we finally obtain the posteriori estimation, posteriori means, and the velocities here, and posteriori strain here, and we reconstruct the configuration by the exponential map or the Kalman map to obtain the posteriori estimation of the configuration. Here we give an example of the geometrically exact beam. We collect the data with stochastic noises of a beam, and we want to estimate the true states of the beam. This is a pure rotation of a beam, and you can. This is the estimated total energy, and estimated total energy, error in estimated total energy, and error in some structures. So all in all, we established estimation algorithm based on variational integrators, and we have some possible future directions and some important issues we want to tackle, like stability analysis and filtering via stochastic variational integrators. Finally, we would like to thank Professor Donghua Shi and Dmitry Zenkov for their valuable comments and suggestions. Thank you, everyone. Thank you very much.
Yes, please. Yes, a question relative to the implementation of your algorithm. As you know, a Kalman filter is conceived to be on board. Therefore, you have the constraints on real time with the computer. So, did you look to this problem?
Sorry.
You presented numerical experiments done in the laboratory. Now, if you wish to implement your filter on the satellite, you have these constraints of real time. So this is my question. Did you consider the real-time constraints for the implementation of your algorithm?
Thank you. Yes, we compare our method with previous works in the performance of real-time performance, and we've it is not presented here, but we found that the estimation, the time of need for the estimation of our method is much less than previous works, because we use the variational integrator. It's a computationally efficient scheme. Thank you.
Thank you.
Yeah, thank you. So what is the assumption on how your noise enters the system? So it looked like from the derivation, the assumption is that the noise enters normally distributed in the Lie algebra.
Yes.
And is that realistic? I mean, because then it's mapped by the exponential map to the Lie group, and then it's not normally distributed anymore, but distorted by the exponential map.
Thank you. Here we use the normal distribution or Gaussian distribution on the Lie algebra, and because our propagation equation is totally on the Lie algebra, so we need the Gaussian distribution of sigma points in the Lie algebra. But previous works use Gaussian distribution on the Lie group, but that's computationally complex.
Okay, so it has computational motivation.
Yes, yes.
So you do all filtering on the algebra and you just reconstruct it on the Lie group?
Yes, yes.
So you did all filtering on the Lie algebra, and then you just project yourself on the Lie group. So this is the principle.
Yes.
Okay. Do we have some more? If not, thank you very much for your interesting talk.